Congratulations, Algebra Express. You were just taking your first test, and now we're starting on material for test 2. So we are in Marecek 3.1. We are going to start graphing today. So today we're graphing linear equations in 2 variables. So the first thing that they even give us is to determine if something is a solution. So this first problem says determine whether the given points are a solution to this equation. So we have 3, 2. We have 3, 1. And so I want to talk about first, what is a solution? I want you to answer that question. So what is a solution? Well, a solution is a number that makes the original statement true. And so when we have one variable, we had one number for our solution. When we have multiple variables, we're going to have multiple numbers for our solution. So a little bit about that. We want to put them in a certain order. So for these things, for 2 variables, the solutions look like things called ordered pairs. And ordered pairs are in the form of x comma y. So the first thing you see there should be your x variable. The second thing you see should be your y variable. And so we look at this. And so they're giving us basically 2 sets to try out. And so this is the first set I'm looking at. This is the second set I'm looking at. And so we want to see if these things are solutions. And so I've kind of already asked the question, well, what is a solution? It's something that if we go and plug back into our original equation, it is going to make that equation true. And so we're going to do that. So if we take 3, 2 and plug it into this equation, 3 comma 2, so the first thing I see there is y. So my y value for 3 comma 2 I have a negative 1/3, and I have to multiply that by x, which is 3. So this is my x, this is my y that I'm plugging in. My x is 3, and I still have a plus 2 out here. And so we're going through, we're checking this thing. So I don't really know if this is equal. Maybe I want to throw a question mark. I don't really know if that's equal. That's what I'm trying to figure out. Trying to see if this is a true statement. And so this side is 2. I think we really need to work at this right side. So 3 times a negative 1/3, that should give me a minus 1. If I add 2, this side is giving me 2 minus 1 is going to be 1. This side is going to be 2 all the way down. So with, let's move this up just a little bit. So if we're looking at this, this is not a true statement. And if this is not a true statement, then this thing is not a solution. So sometimes I abbreviate solution SOLN. So that's something I commonly do. So maybe make note if you see that, that means solution. Okay. So this thing 3, 2 is not a solution. Okay. All right. There we go. So 3, 2 is not a solution. What about 3, 1? And let's try 3, 1. So we're going to try 3, 1. We're going to plug x is 3, y is 1. So the first thing I see here is equal to negative 1/3 times x, which is 2. And then if you add 2, so the left side is 1. The right side is the same thing from the previous problem, so let's see. Hold on, sorry. Messing up your brain trying to think about that one. But it is there from the previous problem. We do 3 times a negative 1/3. I know I did a little quickly. I can always do that 3/1 sort of thing. 3/1 times 1/3. That's just a big fancy 1. There's a negative there. I do negative 1 plus 2. That's going to give me 1. And so this, what does this say? So this is a true statement. So 3, 1 is a solution. So this is one of the solutions. Okay. So what? Well, we're not graphing these things yet. Let's get to graphing some of these things. I think it's the next thing, right? Maybe, well, I can ask the question. Maybe not expect you to answer it right away. How many solutions do these things have? How many solutions, possible solutions, can we get? Okay, so we did number one. Number two. So number two, make up values for one variable and plug them in to find the other. So this section, this entire section where we start graphing things, where we start graphing linear equations in two variables, we're going to graph lines, and we're going to graph lines without using slope or y-intercept or any of those sorts of methods. We're just going to make these things called t-charts. And so we're going to fill out these t-charts with coordinates, and we're going to plot a few coordinates and connect the points. And so there are other ways to draw lines. We're not there yet, is basically what I'm saying. You know one of those other ways? Good. You can use it if you want. I'm not saying you can't use it, but that's not what we're doing in this section quite yet. Okay, so let's go. We need to plug things into this formula, this original one from number one. They're still using the same formula. So if I'm making a t-chart, what I really want to do, almost what I'm always going to do, is throw in a 0 for x. It's one of the easiest variables to plug in and figure things out. So if I go back up here, I want to do where x is 0, and I want to figure out what my y coordinate is going to be. So in order to do that, I have to take this y equals 1/3 times x plus 2, and I have to plug in 0 in place of the x. And if I do that, a lot of things disappear. Plug in 0. It's a pretty easy number to plug in most of the time. So this is giving me a y value of 2. So when my x is 0, my y is 2. Okay. So there are a few different numbers that you can plug in. You can plug in for y and try to back solve for x. This equation is really set up just to solve for y, to plug in an x and solve for y. So I'm going to try plugging in x values, I think, is the best sort of approach on this one. Another thing, what I'm going to do, and what I kind of suggest like might help you, you have a fraction here. If you want to get rid of a fraction that has a 3 in the denominator, then a good thing to make your x be, I think the first one is obvious, like it should be what, 3 and a -3 maybe. Ooh, I'm running out of room on my t-chart there. I'm going to draw it again. Okay. So let's look at this thing. So if x is, let's try just a +3 first. So we're not messing with so many negatives. So if x is a +3 and y is what, -1/3 x. Plus 2. So instead of x, I'm going to write that value of 3. If I write that value of 3, my y is going to be equal to 3 times -1/30, -1 plus 2. And I think we did this already, actually. I could have just pulled it from that first problem. Because when x is 3, y is going to be 1. That was a solution we found. And so maybe I did a little bit of extra work here. Because I already had this from problem 1, right? They told me 3, 1. So I could have thrown that down. So I found that point twice now, I think. So hopefully you've got that point. So this is this problem. So we're finding point by point by point is what we're doing. And then we're going to plot them. So this is x equals what? Minus 3. So we're plugging in x equals minus 3 into y equals a third times minus 3 plus 2. This is a negative negative. This is going to become positive 1 plus 2, I believe is what this is giving me. So my y should be 3. So when x is a minus 3, this thing is 3. And so if you do 3 and a minus 3, maybe you're catching the pattern, maybe not. But what we're doing is multiples of 3. So another good number to do would be like maybe like minus 6 and 6. Okay, so if I want to do minus 6, it's y equals times minus 6 plus 2. Whew. 6 divided by 3 is what I'm doing here. I believe it's going to be 2 plus 2. 4. And if I do what, positive 6 now, times 6 plus 2. 6 divided by 3 is going to be minus 2 plus 2 is going to be 0. So this should be 6, 0. So I have my x and my y, and I have what, 1, 2, 3, 4, 5 points. Okay. So you might be asking, like, how many values do you need to get? Well, technically, we're doing a straight line. The least you need, like, to be able to do a straight line is on 2 points, right? So in order to get a good line, you should probably be doing at least 3 points. So I know I did a few more, but I just wanted to work through a few examples, right? Okay. So we have our T-chart. We have this thing. And now we want to plot these points. And so I'll talk a little bit more about the other thing. I just want to get these points plotted right quick. It's going to be small. We can do it. One through, I can do it. So minus 6, 4 is the first thing. So my x is minus 6. So this tells me left. Ooh, let me move it over a little bit. This tells me left or right. This tells me up or down. So I always do this guy first, and then I go to this guy. So I'm going to go left 6, and I'm going to go up 4. So let me bring it in. I'm going to go left 3, and I want to go up 3. I want to go, where am I? Not left or right, but I want to go up 2. I want to go right 3. Up 1. And I want to go right 6 and up 9. Coming up with them points. And if we want to draw this thing, and hopefully you have a ruler that declares your social status. So, if not, they are fairly cheap. Okay, so it should be going through these points. I know it's not directly on them. Here's an age-old geometry trick. Oh, I missed my point a little bit. Now I make my point a little larger. Oh, look at that line goes perfectly through there. So, sorry, that's horrible. You really shouldn't do that. But I've seen professional geometers do it, so if they can get by with it, as long as your points are correctly, is like I'm not expecting perfection. I'm definitely not an artist, and I don't expect you to be one. So what does this represent? So let's go back and think about what this represents. This was a solution to my equation. This was a solution to my equation. This was a valid solution. This was a valid solution. And this one, so all 6 of these things, these points were valid solutions. I connected these points with a line. So what does this line represent? Well, this line represents everything that is a valid solution to this equation. And you might notice, just from your history and math, you might remember that this is a linear equation. So it hopefully is not a surprise that it's producing a straight line. And so this line represents all the solutions to that equation. So I asked a little bit earlier, like, how many solutions does this thing have? Well, another analogous sort of question would be to ask, how many points are on this line? There are infinitely many points on this line, right? We can pick any point on this line and plug it into that equation, and it should make it true. And so there are, like, technically infinitely many solutions for this thing, right? And they look like everything that's on this line. Okay. So I want to go back a little bit over just like where this graph came from, a little bit over the vocabulary. So you probably saw here, this is called the Cartesian coordinate system. We have 4 quadrants that go counterclockwise. So this is 1, 2, 3, 4. You might notice your X and Y are both positive here. So sometimes they'll go positive, positive, right? This is where my X is negative, but my Y is positive. And this is where they're both negative. This is where they're positive and then negative. Whew, that's the one I'm missing. We go right and then we go down, right? We go right and up, we're going to be in the first quadrant. We go left and up, we're going to be in the second. That's another way to think about that. So where did this quadrant system come from is the next question. It's right here, right? Cartesian. So this word Cartesian comes from this guy, and I think I've talked about him briefly. Rene Descartes, right? And so Rene Descartes, if you go look at mathematicians, old mathematicians, they almost all of them were some sort of like philosopher and delved into philosophy to some degree. And so this guy was no different. He was also a philosopher. He said this phrase in Latin, it's like cogito ergo sum, I believe is how it's pronounced. And basically what it means is I think, therefore I am. And so he was having like a bit of an existential crisis. And there's a bit of a debate among philosophers whether people even existed. And so his sort of rationale to justifying his existence was that well, I don't know whether I exist, and I am the object that is wondering. And so since I wonder, therefore I am, right? And so since you can wonder about your own existence, then you do exist, is what his argument was. So a little bit about the history of this. There's in a lot of history, there's a lot of history. We don't know whether it is really true or not, right? It's kind of a fabled sort of legend. And so I want to start by looking at my ceiling. And so I have a ceiling that's composed of ceiling tiles here. And what happened with Rene is he was staring at his ceiling, probably trying not to think about math. Probably like, he probably just took a test is what happened. And he was probably like, I don't want to think about another math problem ever in my life. And so he's just like, I'm just going to stare at the ceiling. But then this fly came along. Bzz, right? You get sound effects today. And so this fly comes along. This fly, the fly moves. So he sees this fly and he says, well, I can tell you exactly where this fly is by counting the tiles, right? So this is like 1, 2, 3 to the right. And I go 1, 2 up. So he created this sort of system of like describing where this fly is. And then furthermore, if this fly moves, right, it can go like this, come up here, come up here. I can track his movement. And I can create these sort of lines on here, right? And so this is the basis of the Cartesian coordinate system. He saw a fly on the ceiling, and he said, well, I can describe where the fly is by how many tiles it is this way and how many tiles it is that way. And so we look at this thing, and this is the Cartesian coordinate system. I hope in general, like this thing sort of makes like sense in a logical sort of perspective, right? When we talk about one-dimension numbers, like single numbers, we make our number line sort of like that, right? And this is our, maybe we're talking about a single variable x. And so if we want to talk about two variables, like we have a number line and we have another number line, and we just kind of have to determine which sort of orientation we're going to put that thing in. And so essentially what we're doing is we're taking another number line and we're making it up and down. We're making it square to this thing, right? And so another way that you might hear the Cartesian coordinate system described is that it is a square coordinate system. And these squares really come in handy when we talk about geometry, because we know a lot of things about squares, right? They are really nice figures to work with compared to other figures. And so there's a sort of just like logical extension of we have a number line here and we have another number line here. Ooh. Well, no, here's the 0. Sorry. This would be like what? -1, -2. I'm like trying to cram these things together a little too much. And so maybe the orientation's a little weird, because positives go that way, negatives go that way. But it's the same sort of thing. And a little bit, a tidbit of it. Doing programming, they invert the y-axis. So if you're doing like programming, they're going to completely invert the y-axis, and it kind of makes sense when you go into programming, because when you read things on a page, you read things left to right and from top to bottom. So it makes sense to progress as you go down the page. So there are people that do things differently sometimes, right? Being able to adapt is a worthwhile skill to have, right? It's a valuable skill. So did I cover everything here? Cartesian coordinates, Rene Descartes. I think, therefore I am. There's a lot of variations of that one. Okay. So the square coordinate system is what we're talking about. Okay, so I think I might have cheated our way around this thing. Find the x and y intercepts from the previous graph. So if we look at this thing, can I get them both on here at the same time? Maybe, maybe not. Ooh, here we go. So we're looking at this thing. What is an x-intercept? What is a y-intercept? An x-intercept is where it goes through the x-axis. So my x-intercept would be here at this value where x is 6 and y is 0. So this is my x-intercept. The other thing would be where it goes through the y-axis would be my y-intercept. And so that is this thing right here where my x is 0 and my y is 2. So you can grab them off the graph. The other way you could have grabbed them was by looking at the t-chart. We had the point 0.02, and I don't have it on this t-chart. It's on here, down here at the floor. The other thing I had was what, at 6.0 was the other one, right? And so I could go back and look at my t-chart, and I could get the x and y intercept off of that thing. And a little bit about this. If I'm asking for an intercept, what I really want in the format I want it in, and I know you guys understand this, but you don't always give it to me in this format. I want it in the format of an ordered pair, of a point. If I'm talking about an x-intercept or y-intercept, I'm talking about a point on the graph. I really want the two numbers there. I want 6, 0, and I want 0, 2. Okay. Oh, don't read this one. Okay. Find the x and y intercept for this equation now. 3x minus 2y equals 12. Plot the intercepts and use them to graph the line. And so let's pretend like maybe this isn't there. So if you didn't know how to find an x and y intercept, what do you know about them? Well, let's look at the y-intercept. So my y-intercept, it has some number for y, but always, if I want to find a y-intercept, I know my x is always 0. So I can always figure out what my y is by plugging in an x is 0. So if I want the y-intercept, my x is 0. If I want the x-intercept, my y is 0. So how do you find the intercept? You set the other variable equal to 0, and you solve it. So if I have 3x minus 2y equals 12, if I want to solve this thing, I go 3 times, I'm plugging a 0 into my x, minus 2y equals 12. That thing's going to simplify to 0. 0 minus 2y equals 12, and I get y is what, minus 6, I believe. And so just to kind of recap, if I ask for the x-intercept, what I'm really looking for, oh, I'm sorry. If I ask for the y-intercept, what I'm literally looking for is the point 0, minus 6. And so this is should be my y-intercept. And if I want the x-intercept, I set the y equal to 0 and I solve. So 3x minus 2 times 0 equals 12. So 3x equals 12 is what this is going to give me, or x is 4. And to recap, I want 4, 0 if I ask for the intercept. Okay. So technically, we only need 2 points to make a line. And if we do this, if we find the intercepts, guess how many points we have? Okay, I'm not going to put numbers on this thing. It's taking too long. You can count. We're going to do one by one. So if I want to do 0 minus 6, I want to do 1, 2, 3, 4, 5, 6 down. 0 left and right, I'm going to go 6 down. My x-intercept, I want to go 4 to the right. 1, 2, 3, 4. I want to go 0 up and down. And I have my 2 points. Bring up your ruler, social. And that line as straight as possible. I suppose you can also probably use a credit card or a social security card. Just make sure you get a good camera view of it for me, okay? And then we never saw him again. Okay, so if we want to graph a line, we can absolutely just get the intercepts and plot a line between the intercepts. Oh, man. And so I'm going to go on a little bit of a rant. Graph here. I'm going to do it like right in this corner of this graph. Sometimes people will plot some points. Not like those points, right? And they'll do this thing. And then they'll end the graph like right there. Oh, man. Don't do that. Don't do that. Don't do that. Like, keep drawing your line all the way through your graph. And I know, like, maybe it's like, eh. But what if a future problem, they give you a number way over here, right? If you're just, like, drawing your graph like this, you're not going to be able to see all this. Like, you're not seeing a lot of what you really should see. So, like, extend your graph throughout extend your line throughout the graph is what I meant to say. Okay. So make sure your line, like, goes, right? And I'm not trying to be super picky on that, but it's more to do yourself a favor, I think. And it doesn't look pretty to me. Sometimes when you keep your professor happier, they grade a little easier, you know. What goes around comes around a little bit. Okay, so we want to graph a few things, and I've already graphed a few things, and so this is a student activity. So hopefully you're trying, like, by this point to do these on your own. You should be able to make your own little T-chart. So make a T-chart. Put a few X and Y values in there. And so I threw a few X and Y values in there. So if I throw a 0 into my X, I'm going to get the point 6. Minus 3 times 0 plus 6 will give me 6. If I throw a minus 1, I guess I'll perform this one over here. Y equals minus 3 times a minus 1 plus 6. This is 3 plus 6. This should be 9. So I'm going to do a few points. You don't have to pick the same numbers I pick for my X's. You can pick different numbers. This one didn't have any fractions, so picking multiples here shouldn't really be like an issue. If we do minus 3, I believe this should give me 15. And this should give me 3, and this should give me a minus 3. So we did those. So I plotted these points, and then I noticed I didn't have my intercept. So I could always find my intercept if I want. So if I plug in 0, you might even be able to guess where the intercept is just based off of the numbers I have. But if we plug in 0, I'm going to get something 0 equals a minus 3 plus 6. So I'm plugging in where y is 0. And I want to solve for my x. Ooh, and I already dropped my x out of here. It should be a minus 3x plus 6. So move the 6 over. Minus 6 equals minus 3x. X should be 2. So this thing should be 2. And hopefully that makes a little sense here, because between 3 and a minus 3, that's going to give us 0, right? And between 3 and 1, it should give us 2. So we got a few points to plot. We can plot them. So let's do what? 0, 6. 1, 2, 3, 4, 5, 6. And 2, 0. I can also do like 1, 3. Three minus three. Some of these might be a little further to plot than others. And we can get back to our sparkling moon, declare the social status, and let's get marking away. Try to get it as straight as possible. Not gonna be enough. But it's there. And so a little bit about this, like I said, like I am not a visual artist. Well, I am not a painter or a drawer or sketcher or any sort of visual art of that sort. I can make some stencils, maybe, but that's about it. So I am not expecting you to draw a straight line, is what I'm getting at. So I hope, well, not I hope. I'm going to look at your points. If your points are there and they look good, that's what I'm really concerned about. I'm not concerned that everything out here is going to be exactly on the points, right? Because if I look at this, what else do I have? 3 minus 3, minus 3, minus 1, 9. Does it go through there? Yeah, it probably does, right? So I guess that one hit. But they don't always hit. It depends how straight you draw your line. And to be honest, like, drawing stuff by hand is not accurate. Like, if someone gave me this problem, we're learning how to do something here, right? If someone gave me this problem, this isn't the way I would go about doing it. We're learning it this way to get at something else, right? But if someone gave me this problem as as something that wasn't teaching a class, like I would just go plug it in to Desmos, right? And then it would give me a very accurate sort of description. It would give me very accurate points. And if not Desmos, I would use my graphing calculator, use some sort of technology to graph this thing is what I would do. Because technology graphs things way more accurate than I could ever draw, right? So this one. I want to try to like maybe save down a little work. Let's just do those unit tests. Let's try to do those unit tests. I got an X and a Y. If I plug in 0 to my X, I have 3 times 0 minus Y equals 0. A minus Y equals 0, which means a positive Y is also 0. If we negate 0, it's still 0. It does not change, right? Okay. So what happens if I plug in 0 to Y? Well, I get 3x minus 0 equals 0. I get 3x is 0, or x is 0. So I'm still getting 0. If I plot this is, I'm going to plot 0, 0, 0, 0. Uh-oh. That's not going to give me a line. So I have to do something else. I think what I did, I think I plugged in 2, I think I plugged in a minus 1. So we plug in a minus 1 to the x, 3 times minus 1. Minus y equals 0. That gives me a minus 3 minus y equals 0. That gives me minus y equals 3 when I move it to the other side. And so if I multiply by minus 1, y is a minus 3. And now I want to do the x value of 2. So 3 times 2 minus y equals 0. So 6 minus y equals 0. And we move the 6 to the other side. Y equals minus 6. These are both negative. We multiply by a negative. They're both going to become positive. So I get y equals 6 for this thing. So if I do a minus 1, 2, 3. If I do 2, 2, 3, 5, 6, So I draw these 3 points. Try to jump. Okay. So there is something I skipped past that I want to go back to. We want to have something, I had something that looked like 3x equals 0. And if we have something like 3x equals 0, in order to get to the next step, we have to just divide both sides by 3. And so now I think this comes into the question of like, is x equals 0 over 3? And that is, I've already said it, so you probably know what it is. But 0 over 3 versus something like 3 over 0. How do we know what that is? Okay, so let's, the way I think about it is pizza and people, right? If you have a party, pizza to people. Pizza to people. If I have no pizza and there are 3 people at the party, guess how many slices of pizza each one of those persons is getting? They're getting no pizza. You can do that. You can have no pizza at a party. That is, it's not a fun party, but you can do it, right? If we have 3 pizzas and there are no people at a party, I'm hurting myself asking this. There's no people at the party. How many slices of pizza is each person going to get? If someone asked you that question, you would probably look at them really funny, like, what the heck are you asking, right? There's no people here. If there's no people, how can you even ask that question? And so this thing does not compute. It's undefined in math. So 0 over 3 is 0. We can divide 0 evenly into however many people. We can have no pizza. Each person's going to get no slices of pizza. We can have 3 pizzas and no people. And then you're just asking silly questions that don't even make sense, right? So this is sort of like the first commandment of math, right? Thou shalt not divide by 0. You unravel the universe, I think, is what happens. Okay, so that is a student activity. So we're getting to horizontal and vertical lines. So now we're looking at this equation x equals 5. And so you might be looking at that like, I thought this section was about variables with 2 equations. And you're right. So let's think about this. Consider the equation x equals 5. So I have my t chart, I have my x, I have my y. My x is 5. So what does that mean? What does that mean with my y? It says it right there. Oh, let me take all the fun away. There's no restrictions on the y. You can literally plug any number you want. You can do minus 10, minus 3, 0. You can even do weird things like pi, right? Good luck graphing pi on a Cartesian coordinate chart, but okay. So what does this mean? This means I'm going to go right 5. 1, 2, 3, 4, 5. 5, 0 is a point. So hopefully I counted those right. That should be 5 to the right. And I go 5 to the right, and I can go up and down, and I can go up and down as much as I want. It doesn't matter what value I pick for my y. And so you might notice this line is looking something like this. And so this is the x equals 5 line. And so we want to know, I'm horrible with these words, so I can almost guarantee you I will mix up vertical and horizontal at some point. And y'all can all point and laugh and call me out on it because I really need to stop doing it. But horizontal goes with the horizon. Vertical is like when you're leaping up and down. So which one is this? This one is the vertical. It is the vertical line. So things that look like x equals gives you a vertical line. And I feel like I could go do a SAT analogy question, right? If x equals gives you a vertical line, then y equals is going to give you, oh, let's not go too fast. Okay, this is x and y. Y equals a -3, which means we can plug in a -3 into these things. We can do anything in our x. So this is very similar, just flipped, right? Now the y can be anything, or now the y is always a -3 and the x can be anything. Let me say it the right way. Okay, so we want to graph this line. We want to go down 3 and we want to go left and right as much as we can. It doesn't matter which way you go, what number you go to. We're going left and right all the way. And so this looks like y equals a -3. And this is producing something that looks like a horizon. And so I want to go over maybe like something that's a little weird. Because those are x lines. If you think about the x lines, and this is sort of the way that I was talking about it, we're creating a graph sort of thing, right? We'll talk about x value. And I think this might be one thing that trips people up a little bit, is that when we talk about x values, we talk about how far left and right we go. But when we talk about the x line itself, it goes completely vertical. So it measures left to right, but in order to measure left and right, the line itself has to go up and down, right? Sort of like latitude, longitude sort of things. If it's measuring what, up and down, the lines are going left to right, right? Well, I said that backwards. If it's going left and right, the lines are going up and down. And like with the y, it's very similar, right? We have a y equals 0 here. We have a y equals a -1 down here. And y equals 1 here. We're creating a sort of square coordinate system with these things, right? And so the y values, they measure up and down, but the lines themselves go left to right. So going back here, our x's measure left to right, but the lines themselves are vertical or up and down, right? The y's measure up and down, but the lines themselves are horizontal. And we're almost there. 2 little things we gotta answer, right? And so we're looking at this thing. And they say something about find an equation of vertical line through 5,2 and find a horizontal line through 5,2. So I've got my coordinate system. It's got a 5 here, it's got a 2 here, and I'm drawing, right? So if you need to draw a graph, you can draw a sort of graph for this thing. And if I want to do what? The vertical line, I draw a vertical line through that. What is my vertical line going to be? I'm hoping you're telling me this thing is x equals 5. So I believe that's the first one they asked for, is the vertical line. X equals 5. And then the next thing they asked for is, what is this horizontal line? This horizontal line is y equals 2. Okay, so this thing should be y equals 2. So we did a lot of work. And if you need to draw the graph, you can draw the graph. But technically you shouldn't have to draw the graph, right? If we want a vertical line, I know vertical lines look like x equals. And if I'm looking at this, if you tell me x equals 2, I can tell you right away you're wrong, because that's the y value, right? So if you want vertical, it's going to be an x line. It's going to be the x value that you have there on your point. The y value can change, but the x can't, right? Same thing here, just vice versa, right? The y can be 2, but and it always has to be 2 if it's horizontal, but my x can change left and right, so it's a constant of y equals 2. And I believe the next section we start talking about slopes. We can talk a little more about these things in terms of slope as well, but not till next section, right? And I think that does it. So hopefully y'all watch this video. I can see you on Friday, and we can start on test 2 material. All right, good luck. See y'all soon.